Cannot hear me, case. Let me quickly check that. Actually is enabled microphone wise. Pum, 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 pum. 1, 2, 3, 4, 5, 6, 7. Okay, so now hopefully now it should be better. Okay, now I lost my mouse. Okay, I've got my mouse. Okay, so let's try it again. Welcome to Iron Middle episode number 100, which is 101st episode. And I have a cool announcement to make is that I kind of like got annoyed with the fact that Twitch isn't working for some of our viewers. So what are we going to do starting from the next episode is actually to stream this thing to more platforms. We probably will go with YouTube and X. So if you want to see this live every Thursday at 5 p.m. UTC, you will have more options than just Twitch. And of course, as usual, you could always watch the recording on YouTube when it is released shortly after it is live. But it's always nice to watch live because you could ask your questions in chat and I will answer. Okay, so what are we up to today? I think we are up to refactoring the core loop of zigzag merge. That sort of refactoring that threw me into like the deep end a while ago, which promoted us to do multiple refactors everywhere. But before we do that, I want to explain what zigzag merge even is. I still haven't read any papers about that, but I think I've watched enough bits and pieces to understand the core idea. So let's go to some sort of where is this? Okay. Yeah, so we have our TL draw with some kind of stuff which we did, and will now figure out what the heck is zigzag merge. So as you might guess from the name, zigzag merge is a kind of merge algorithm. So we have a sorted array with like numbers. Well, actually, no. I don't want to draw this because I mean, this sorted array. It's much easier to explain in code. So let's rather do this. Let's call this zigzag. So let's go dark. Okay. So let's imagine that we have some sort of sorted array I want to make it slightly bigger. Yeah. And something like 23, 190. Yeah. So you could imagine, like, you know, your, oh, wow, I actually need to set up my screen sharing. Okay, yeah, now you should be able to see what I want you to see. Okay, so we have this sorted array, and you could imagine like set of sorted arrays, and you could imagine, like, you know, a merge algorithm which yields 1, 1, 1, 3, 6, oh no, 3, 4, 6, 7, 8, 9, 9, 9, 10, 11. Yeah. So that's how would you like your normal merge algorithm would work. For query engine in a database, we are actually interested in something slightly different. I guess we are going to have 2, 6 here. We're interested in something slightly different. We are interested not in the union of all those things, but in their intersection. We only want to output the numbers which are repeated in every single array. So we want to output 1 in this example because it is everywhere, and we want to output 9 because it is always everywhere, but nothing else. So this is our output of zigzag merge. And how are we going to do this? Well, let's maybe start like more interesting example. Like how we find, so here the answer is 9. So how we find the 9? We start with pointing to a first array and noticing, hey, we have a 3 here, right? Then Okay, let me do this. I have this nice overtype mode, which should help me. Okay. So then we move our pointer to the next array, and we see that, hey, this is 6. So we change this to 6 because, okay, we know that definitely 6 is not the right answer here. 3 is not the right answer because in the next array we have an element bigger, and because every array is sorted, like we will never see 3 in this array. So now we again move I have this fancy overtype mode, but I am not used to it. So here again, we move to the next array, and now we point at it with 6. Now we see 1. So we might actually, it might actually be the case that there is 6 there. And to make this more interesting, let me do something like this. Yeah. So we know that the smallest candidate number we are looking for is 6. But in this array, the first number we see is actually 1. So we know that we need to skip past 1, past 2, past 3, and past 5. And what's more, because we already know that we need to skip all the way up to 6, we don't actually because we won't skip all the way up to 6, we don't actually need to skip 1 by 1. We could binary search 6 in this array and go there. So what we'll do here is that we will essentially leapfrog all the way up to 9 and change this to 9. Okay, now we wrap around and go here. And again, the same sort of situation appears. We are looking for 9, and here we have 3, so we can leapfrog to 9. And now something interesting happened. What happened here is actually we now know that we have 2 instances of a 9 here. So then we move again here, and we again leapfrog it all the way up to the 9. And now we notice that we have 3 9s, and that is the number of items we have, and we could like output 9 as a next item. So that's essentially oh no. This is essentially what happens here. I want to reset why is it working? Anyway, so this is essentially like a zigzag merging. We kind of like go through these arrays one by one and like always trying to jump to the next item. We implement this algorithm in this pick key function, and I kind of like feel that this is not the best way to do this because it has like some kind of like bit sets and loops and whatever, and we know that we know that this is enough to confuse me, because the last time I tried to tactically refactor this code, I kind of got confused. But right now, I see where my confusion stems from, because you see, like the way you could visualize this zigzag merge is that you just go like round and round and round. While here it's kind of like we don't go around, like we start and then restart, start and then restart. So I actually want to go and try to write a second version of this function. Maybe it will be better, maybe it will be worse, but I'm just interested if we could pull this off here. And I need to disable my fancy overtype mode. Oh, well, yeah, but actually I need to also explain this pendant thing, because that's kind of like was like, you know, an easy part. The hard part here is that at some point you will see the rest is on different block on disk. So at some point you'll see, hey, kind of like we know that the array is not finished, but we actually need to do more disk I/O. So if we let's see what we like in this situation. Something like this. Yeah. So well, let's let's see that this is 137. Okay, yeah. So let's see that we are in this picture. We know that like the current candidate is 9. We are currently pointing here, and we know that there is the continuation of this array, and it's on disk. For this array, we actually know that this is the real end of data. There is like no more. Let's actually like call it U. So if we like do this naively, what we'll do here is that we'll jump through 7, and then you realize, hey, actually to probe further, well, we sort of need to go to disk, and we say, okay, so let's see and read the disk and see if, like, you know, the next number is 9, or maybe the next number is 8, or maybe it is 10. We don't know. But that's going to be suboptimal, because you see, we are interested in cases where the element is part of all arrays, including the arrays we have in memory. And by just looking at this output, you see that actually, like, the output here is null. There aren't any more values that you need to do, because you could actually just skip this one, and then like, actually, okay, no. Let me create this way. So here you'll jump to 23, and then you'll jump to 25, and then you'll jump to 119, and then you jump to end of file, and you realize, hey, actually, no. Even without reading the rest of the stuff from this, we can say that, hey, the result of your query is empty. Okay, so that's what this pendant is doing. So we might return an next key which belongs to all the streams, or we could return null, which means that there is no more keys which belong to all the streams, or we may return pendant, which says that, hey, actually, we gotta read data from this to figure out the answer. So, and the way I want this to work is actually to, well, obviously we'll need these asserts. And well, I want to flip those around because I actually want to, like, do a proper like trisection there. Like basically, I want the assertions to be in the same order as they are on the number line. I want to see first one, then string count, then strings max. Then I have k over. Let's call it sentinel. I don't want to call it mean because it actually depends on direction. And we did merge this direction. No, we didn't. Wait. Why is this? Such an old looking code. Wait, what? Ah, wait. We do have direction merge, right? No. We didn't merge this pull request due to some nonsense in Rust dependencies. Okay, that's not good, but hopefully it will merge. Okay, let's start. Let's just start with that. And then, okay, it still came in, but now, okay, now the direction is what we want it to be. Pick k2. Lower. Oh, let's call it k lower because that's the terminology we established for direction. Okay, so what I actually want to do is that I want to do, like, a tour around all the streams, which is going to be round and round around. Okay, we'll figure out the comments later. And I want to do something which I don't usually like. We never usually do it. Target, like, start with while true because I do want to add a certain upper limit to this loop. But let's start with while true. So key lower. That's actually called Sentinel. So what we want to do is that string big wants string index wants u32 to our index. So I want to string big index to index. Okay, so I kind of like I do want to copy paste the code. So I'm looking at the current stream, and yeah, I might get an error, or I get a null, in which case I want to return null. So if we definitely reached the end, then okay, this is the end of it. Okay. Otherwise, I got an error. Which means I need to do something, but let's just say to do here. Okay. So, okay. Let's call this candidate. So now we could write comparison. If it p candidate. Okay. Then our current key becomes a candidate, and we need to reset the tour. So let's say we also have tour tar index. Else we continue the tour. Well, actually, let me maybe write this slightly asymmetrically. So actually maybe, so here we should do stream probe, right? We need to do stream probe, and then we need to do something, but let's just start with stream probe because it feels like it's just better, right? Context. How do we call it? Stream probe or index probe candidate. So actually here we can assert that candidate is before the key. So I'm trying to like reduce special cases. Okay. Else. So else we kind of extend the tour. Let's tour length. Tour length. Okay. And here I think we also want to do +1 to tour length, because we do want to eventually do like one whole round. So if after this point, we say if tour length is equal to frames count, then we break. Here we essentially do turn candidate. Okay, this makes some sense to me, perhaps. And it is much simpler than existing probe, at least, except that we okay, so we haven't counted like the amount of like pending items. So let's just count pending count. Our pending count if it's 2 equals 0. So we need one full tour, so we break, and then we say if pending count equals 0. If pending count is positive, then we return our pending, and then we otherwise we're talking it. And this is kind of like, I mean, it can be this simple, right? Well, okay. We also need to say that tour index +1 modulates touring count. Frames count. Okay, so this kind of like feels like it might actually be it, right? So we want to pick a next key. We start with a sentinel value, and then for each string, we ask it to go up until at least the current candidate. If we get pending here, we move on. I mean, okay, we don't actually even need walls. Okay, this sort of feels like, hey, actually maybe we don't need separate uh, peek and probe implementations, and like could just, like, just, okay, give me the next value this given given this lower bound. Okay. So we do we break over out of this loop only when we do full Tor, and that means that in this Tor either all items are matching or all are pending. Yeah, and that is good. And if anyone is pending, then we return pending. If all are matching, we return candidate. Yeah, okay. It's actually feels like this might be it. Okay, so let's do like the scary thing and try to compile it. Okay. Tor index, Tor length. Do I want, okay, I do want count, pending count. 32 equals 0. Matching count 32 equals 0. So I want pending count to increment there. I want to reset them here, and I want to so we assert that Tor length equals count, and also want to assert that matching count plus pending count equals Tor length. Okay, yeah. And then if pending count is positive, then we return error pending. And they all are actually probed. So, okay, I think this is a simpler way to write this thing as a single loop rather than as multiple nested loops. But you never know. I mean, like compilers can be merciless. You gotta ask the compiler if it likes it. Well, obviously it likes it because it doesn't really compile the stuff. If I do this, hopefully I should get a compile error expected. Yeah, it's like, you see, it's like always useful to get a collision errors. Okay, yeah, okay. It doesn't work at all. Incompatible types, optional use64 and void. So K is expected to be K. Stream peak. All right, I need to do something here. I guess I need to do continue. Yeah, I don't really love this. Well, okay, let's first make it compile as is, and then we'll okay, it compiles as is. Let's try to refactor execute cannot if it be else or no or now else now. Okay, yeah, so this is kind of like a thing where like nested pattern matching would actually be better, but yeah, okay, I do think I kind of like this better or or now else return now. Okay, no, that doesn't really buy us much. Okay, I'm curious. Like, can we actually figure out whether this is correct or not? Do we have? We do have some past test here, right? Past tests. LSM scan pass. PK2 is that code. Okay, this is actually what we did on video. Okay, let's kind of like work around our tidy failure by just making it public. Okay, I'm really am unsure that this is all we need here. It feels like it might be. I don't even need this like sentinel value. Oh, okay. Well, there was something about probe key previews, right? Okay, it was only the assert peak. I don't really. Wait, what is key port? Okay. And I realized that I actually might want to check how it works. Okay, something broke. Okay. So okay, yes, we could write this for total for pendant and for matching. Total. Okay, now let's play our favorite game of finding good names. Store equal total equal missing pendant matching. Match pendant total equal. Okay, equal total equal. I like this better. Missing read disk to skip then the async. They're not really okay, ready would be perfect, but this is not ready. What it could be then if it is not ready? Tor rest down pause. Okay, pendant. Tor store equal plus store pending. Well, let's write it this way. Total is equal plus pending. Get asserted one more time. Okay. Okay, let's run scanfats. I think we are string index. Maybe we need to build it in release mode. One more time. Okay. Let's actually do our index. Or index times its count. Let's see. It feels like that actually might actually go into like the exact infinite loop, which we want to prevent through okay, maybe not. Oh, okay, it's just compiling. I can't say. Okay, it would be a shame if this instruction fails. Okay, rich sandwichable code. That's interesting. What is that? Oh no. Oh no. Oh no. So why are we getting this? Door index. Well, okay, because we actually don't want to do continue here, right? Because we do want to at least duplicate this line. Kind of like really want to just write it out, right? As I say, we are still stuck here. Okay, now this worked. So maybe. Well, okay. Actually, I mean, let's think positively. The fact that this did fail before actually told us that hey, our fuzzer has some non-trivial coverage here. That they kind of like really do find this duplication ugly. Well, okay, I guess we could just place it here, right? Okay, I kind of like do like what I see here. It's kind of like how do we have any kind of upper bound here though? Don't really have super convenient around. Okay, but yeah, this kind of like looks uh, looks nice to me. Maybe one more time. Yeah. Four. Okay, let's actually do. Oh, can we write a four here? It's kind of like would be really safety countable. Can we easily derive safety count? Well, maybe we could derive it from. Okay, no, I don't really want to have this. Okay, let's maybe leave it at this and write up a comment and a commit message, and then let it simmer for a week, and maybe 1 week later we realize that what are we doing here is like a terrible idea. The actual Zeek exact image implementations. We want to find the next key. That belongs to our stream. We arrange things in Yoko. Boom. Arrange things in Yoko. And order go around the circle, maintain current best guess key. If you make a tour around full tour, everyone has the answer. Okay, computer and various storing targets with key. It is an answer. If image then is using tour, Okay, okay, you don't. I'm not finding the right words here. Candidate E. Ask each student to advance to at least the current date. To at least the current to best as to the day that to be such that key can be date. And complete for without none means that the next common be. Okay, now let's type this. That means that we can delete use the common key. If any string ends, there is any string is exhausted, there are no command. Please return now. A string might also be pending. Let's disabled fetch the next key. Pendants means lead to one side and be okay. No, I'm just going to be here. I realize that I'm not able to like coherently express what we are doing here. So um, go along this circle. Oops. Dreams. Go around dreams until we manage a full. Okay, this is better. Until we manage a full tour such that all streams are equal or pending. Go around the circle. Okay, so let's see. Simplify the knowledge. Okay, let's do this. Let's scan. Okay, zigzag. Well, that's not. Okay, let's see. Okay, I want to. Okay, yeah. Uh, I think this can be this as single loop, though I am but I think deeply of them. Okay, but I think like this is like a pretty. I mean, it is twice. Well, I mean, it's not twice because I've also like removed all the comments, but it does feel like a significant simplification in the big complicated part of the system. So, okay, let's then turn on the light and finally wrap it up. So I kind of like was super unsure going into this episode where we'll book down, or wherever we'll finish in like 5 minutes. But actually, it feels like we did make meaningful progress here, and we did manage to do this refactor, which I think is good. But again, as I wrote in the pull request description, maybe the fuzzer will prove me to be wrong. But even if I'm wrong on like the specifics here, I think there is like this this like useful meta lesson here, is that like you need to be honing on those complicated loops which make you uncomfortable, and you need to try to find a way to simplify stuff, refactor it, condense it, because ultimately your entire big system is just a composition of these small individual pieces of code. So okay, let's call it a day. And as a reminder, you will be able to watch the next episode of Iron Beetle, episode 102, at 5 p.m. UTC, live on Twitch, YouTube, and X, unless we messed up our streaming setup as well. You will be able to tell next week. So, okay, goodbye, and see you in a week, minus 1 hour and 19 minutes. Goodbye.